I hope by now that you have downloaded our free simulator program from this website. It will make it much easier to follow the tutorials as we continue. To gain the full benefit of the tutorial, you should use the simulator to experiment with circuits of your own. An inductor is essentially a coil which may be wrapped around an iron rod. We know that when a current is passed through a coil, a magnetic field is set up around it. This field imparts a voltage, opposing the voltage driving the current. The size of the opposing voltage is dependent on the rate of change of the current. In this example, the current would be 0.9 amps, but this rapid change from zero in the current causes a big change in the opposing voltage. In the first instant, the power source is completely opposed and no current flows. Gradually, the magnetic field decays until there is no opposing voltage. We run the simulator a few times and see the effect. Notice how the current climbs as the inductor voltage decays. We have seen a similar curve before in relation to the capacitor. To begin with, we compare the current curve of the inductor with the voltage curve of the capacitor. We see the similarity. We know that the capacitor's voltage builds up, whereas the inductor voltage decays, allowing the inductor current to rise. Now we compare the current curve of the capacitor with the voltage curve of the inductor. Again, we see the similarity. The unit of measurement of inductance is the Henry. A 1 Henry inductor will allow the current from a 1 volt battery and a 1 ohm resistor to rise to 63% of 1 ampere in 1 second. For smaller inductance, we have 1 millihenry is 1,000th of a Henry, 1 microhenry is 1,000th of a millihenry, 1 nanohenry is 1,000th of a microhenry, and 1 picohenry is 1,000th of a nanohenry. Here are the relevant formulae for current and voltage for both the inductor and capacitor. For inductors in series, the total inductance is simply the sum of the individual inductances. Inductors are similar to resistors in this respect. For inductors in parallel, the reciprocal of the total inductance is equal to the sum of the reciprocals of the individual inductances. Once again, inductors are similar to resistors in this respect. What happens when we combine an inductor with a capacitor? This is a so-called series RLC circuit because it contains a resistor, an inductor, and a capacitor in series with a battery. Initially, the capacitor has no charge and the inductor opposes current flow, so there is no current. Gradually, the inductor allows current to flow and the capacitor charges up. Finally, when the capacitor is fully charged, the current stops. We start and stop the project a few times to see the typical current curve. The previous example was a so-called overdamped series RLC circuit. Now we shall see an underdamped RLC circuit. The resistance has been reduced to half an ohm. We run the project and notice that the current oscillates and finally peters out. The smaller the resistance, the greater the amplitude of the oscillations. The size of the resistor affects the damping or petering out of the oscillations. In fact, for circuits with the sizes of inductor and capacitor equal, as we have here, the damping produces 3 curve shapes depending on the resistance R. If R is less than 2, it is underdamped. If R is equal to 2, it is critically damped. If R is greater than 2, it is overdamped. You can experiment with these for yourself. Here are some useful formulae which should enable you to predict the shapes of curves produced by the series RLC circuit. Using these formulae, one can create a predictable curve. For example, letting R equal 0.5 ohms, L equals 1 Henry, C equals 5 millifarads gives rise to angular frequency equal to 14.14 radians per second, and attenuation equals 0.25, which is low. We introduce alternating current with a resistor and a capacitor. There are a few things to notice about the waveforms created here. Firstly, if the capacitor were not there, because we have a 1 ohm resistor, the amplitude of the current would match the amplitude of the generator and they would be in sync. Secondly, because the current amplitude is less than the generator amplitude, the capacitor must be impeding the current. We call this reactance. The total impedance, or opposition to current flow, is made up of resistor resistance and capacitor reactance. If the capacitor is large, the current is hardly impeded, whereas if the capacitor is small, the reactance is high. So the reactance is inversely proportional to the capacitance. You can try out various sizes and see the effect. Thirdly, if the frequency is increased, we see the reactance of the capacitor reduced. Once again, the reactance is inversely proportional to the frequency. In fact, the reactance of the capacitor is inversely proportional to the product of capacitance and frequency. Finally, because the capacitor takes time to charge and discharge, its voltage lags the generator voltage. We will investigate these ideas more fully. Before continuing, we should remind you that a radian is a measure of an angle. It is the angle formed if we trace the distance of the radius around the circumference of a circle. Because the circumference of a circle is 2 pi times the radius, we can say that a full 360 degrees is 2 pi radians. 1 radian is about 57.3 degrees. A sine wave can be drawn by rotating the radius of a circle and plotting the height of the radius point above or below the horizontal. A single cycle of a sine wave passes from 0 radians to 2 pi radians. As current is arriving in the form of a sine wave, we can predict that the capacitor will charge while current is positive and discharge when it is negative. Therefore, the capacitor voltage will be at its extreme whenever current crosses from positive to negative or negative to positive. So we see that the capacitor voltage lags current by pi over 2 or 90 degrees. We saw that in our last simulator experiment. Alternatively, we can plot resistor voltage against capacitor voltage. Because resistor voltage is proportional to current, resistor voltage is in sync with current. Once again, capacitor voltage lags resistor voltage by pi over 2 or 90 degrees. In our previous diagram, capacitor voltage was at its negative extreme when resistor voltage was 0. We draw two radii representing resistor voltage and capacitor voltage at this instant. Rotating the two, we see that we generate the two sine waves for resistor and capacitor voltage. Try this for yourself. We can go a step further and draw in the vector sum of the two voltages. This represents the voltage at the source because the two voltages must sum to the source voltage. We see that the three curves reproduce the curves produced by the simulator. Notice that current leads the source voltage, which leads the capacitor voltage. The phase angle phi is the angle by which current leads source voltage. This type of diagram is known as a phasor diagram. Finally, we can plot the resistor's resistance against capacitor reactance. Because the current passing through each is the same, we know from Ohm's law that the resistance and reactance are in the same proportions as resistor voltage and capacitor voltage. We show the capacitor reactance as the letter X. The total impedance is found from Pythagoras, and that is given the letter Z. We can summarize what we know in the following formulae.
The source voltage delivered by the wave generator at time t is the maximum voltage multiplied by sine over omega t, where omega is 2 pi f radians and f is frequency in hertz. The reactance of the capacitor is the reciprocal of omega c, where c is capacitance in farads. Now we replace the capacitor in our circuit by an inductor. Because the inductor opposes the source voltage, we expect the inductor voltage to lead the source voltage. We see that this is so. This time, however, the inductor voltage leads current by pi over 2 radians and also leads the source voltage. Through experimentation, you can show that the higher the inductance in terms of henries, the higher the reactance. Also, the higher the frequency, the higher the reactance. In fact, the reactance of the inductor is proportional to the product of inductance and frequency. This is the reciprocal of the reactance of the capacitor.
Here then are the formulae for the AC series RL circuit. That concludes this part of the tutorial. In the next part we will continue to look at the inductor and its alter ego, the capacitor, and will work towards tuned circuits, which are important in radio reception.